Okay. So before I get into what I said I would do at the end of the things, at the end of the last lecture, so what did I do? I came up with an idea, a mathematical expression, and a physical model for where resistance in a circuit comes from. And the expression I came up with was that the resistance in a wire, or anything made up of a bunch of wires, as it turns out, can be calculated by multiplying the resistivity of whatever metal you use to build the circuit out of by the length of the wire that you use and divide by the cross-sectional area of the wire. Okay, and I won't repeat all the reasons why this expression is true, but it is. I want to do a couple of things here, and in fact, I'm going to write myself a note here just to remind myself. I'll put it down here. EMF versus V of battery. I kept promising you I would talk about that, and I don't want to forget, and I'll do that this video. Okay, so let's first of all just do a quick calculation of this. So let's do a quick example. So if I have a wire that's 50 centimeters long, which is not uncommon, a couple of alligator clips will do that, and the cross-sectional area of these things. Now, I don't want to get too complicated into this, but I don't want to lie to you either. Many wires, particularly things like alligator clips, have you ever noticed an alligator clip lead is very, very flexible, and most wires are very flexible. And the reason for that is that the wires that what you think of as the wires with the insulation on the outside and so on are not actually just a single solid piece of wire, but actually a whole bunch of very, very thin wires all stranded and wound up together, sort of braided together. And it turns out that the resistance of that arrangement is actually still very small. Even though the wires are thin, you've got a whole bunch of them. Okay, that's actually something we'll talk about in more detail in a slightly different context in another lecture. But anyway, so you have a whole bunch of these braided wires all in physical and electrical contact with each other. And so from the point of view of the charges moving through the wire, it just looks like one big wire, but it does have the advantage on a human scale of, first of all, being, you can get the same small resistance is physically small, and it has to do with the fact that you're using the external surface area, not just the cross-sectional area of the wires, and a bunch of other things. Anyway, the point being that most wires that you see are not really a single piece of copper. It's not a single copper cylinder, but a whole bunch of very thin wires all banded together. That's all true. It doesn't change the essentials of this calculation. It makes it slightly more complicated if I really wanted to do it, but I'm just trying to make a point here, so I'm not going to worry about those kind of details. Okay, anyway, so the cross-sectional area is effectively, well, let's say your typical radius for such a thing would be about 1.5 millimeters, which is, of course, 1.5 times 10 to the minus 3 meters. And then the resistivity of copper, I mentioned that in the previous one, is was it 1.5? Is 1.5, 1.7? Let's look that up real quick. I don't want to lie to you. Let's see. Resistivity of copper was 1.7. There we are. 1.7 times 10 to the minus 8 ohm meters. Okay, and if I've done anything like a decent job here, we would expect the resistance to be pretty small, because after all, the resistance of copper wires is known to be pretty small. Right, so let's see if we get something small. So substituting all this, we get that the resistance is, okay, 1.7 times 10 to the minus 8th ohm meters. The length is 0.5 meters. The area is pi times 1.5 times 10 to the minus 3 meters quantity squared. And if I do that, and I guess what I'll do is I'll pause the recording, punch that up in my calculator, and come back. So pause. Okay, probably you already punched it up. I got 0.001, and checking out the units here, we expect to get units of ohms. Meters times meters in the numerator gives me meters squared, divided by meters squared down here. Well, I shouldn't cross that out. The 2 is still there because it's still squaring this number. So, but anyway, we are left with ohms, sure enough. And so a very small resistance, as you see, yeah, and so that makes sense. Okay, so that's resistivity and resistance. Again, the resistivity is a property of the material that you use to construct the wire. It's not a property of the wire itself. It's a property of the copper, not a property of the wire. Okay, now I also mentioned, I wrote myself a note and might as well go here and do this first. I also mentioned that there is a small but important difference between the EMF that a battery supplies and the potential difference that the battery supplies, and now I'm in a position to explain that. So in a battery, in a real physical battery, draw it like that, okay, and it's attached to, and then this is your light bulb or whatever it is. Okay. Now, as the current flows, remember we're assuming positive conventional charges making our way through the wire. So the charges start here, flow up, flow through the wire, flow down, flow through the light bulb, cause the light bulb to light. I still haven't told you how. That's coming though. And they flow, but the circuit completes because the charges flow through the battery, like so. So it's the same current all the way around. I haven't justified that yet either, but I will. In any case, but the issue and the reason that sorry, I got to pause recording just for a moment. Sorry about that. So the current is flowing through the battery, but like the light bulb, the battery actually offers up some resistance to flow. There is some internal resistance to the battery, which, I mean, that's not a stunning surprise. I mean, there's a bunch of stuff inside the battery. There's different materials. Most batteries, most so-called dry cell batteries are made up primarily of carbon inside, and carbon has a comparatively high resistivity, and there's other things in there. Anyway, there's internal resistance, but the internal resistance has an influence on the current. It tends to decrease the current, just like the resistance here decreases the current. So there's two contributions to resistance. There's the resistance of your light bulb, and then the resistance, the so-called internal resistance of the battery, which we usually symbolize with a lowercase r. The reason for that is, first of all, to remind us that it's sort of a specialized resistance. It's from the battery rather than anything else we attach to the battery. And the other one is that most of the time, the resistance offered by the battery is small compared to the resistance of anything we're using to actually operate with this battery. But that's the reason there for the difference between the EMF that the battery can supply and the potential difference that the battery actually creates. And that is, if you are not actually using the battery, I mean, if it's not connected to a circuit, then the potential difference that you measure with a meter, the number you will see on the meter screen will be the same as the EMF the battery was designed to have. It's only when you start using the battery and the current starts to flow that the resistance of the battery comes into play, because it's only when a current is actually flowing that the resistance has any effect on anything, because resistance affects only current. Okay? And so at that point, the battery still has its designed EMF, but the potential difference that it, let me say it like this: the current that you see from the battery is related to the potential difference that the battery provides, not the EMF. Okay, that's a little bit confusing, I know. So the short version is that the number of volts that you'll read across the top and bottom of the battery is smaller when a current is actually flowing than it is when a current is not flowing. Okay, and this, by the way, if you've ever, for example, had a battery, you suspect you have a bad battery in your car battery, and you take it into the shop to have them tested, they don't just put a meter across the negative terminal and the positive terminal. They actually have to put it on a machine and put the car battery under load, as they say. What they're actually doing is sending it through a device that has the same resistance as your car engine, so that it simulates the actual current draw that your car engine actually provides without actually putting it in your car. And if the voltage reading across either side of your car battery when it's under load is a lot smaller than the voltage reading when the battery is not under load, what that tells you is that the internal resistance of the battery is very large. You don't notice that when a current isn't flowing. It's only when the current is actually flowing that the increased resistance makes itself known by a substantial change in the voltage reading at the top. What that tells you is that the EMF and the voltage the EMF and the potential difference are very different from each other, which tells you the internal resistance is very high, which tells you you have a bad car battery, which tells you your bank account is about to get a $70 hole in its pocket. Okay? So that's what that is. Okay, so that's the difference between potential difference and EMFs. Most of the time, if the battery is good, then the EMF and the potential difference are essentially interchangeable. And in fact, your textbook, I believe your textbook, you can check, I believe your textbook decides to ignore the small difference between EMF and potential difference. By doing so, they are implicitly assuming that it's a good battery. If the battery is starting to fail, then you can no longer ignore the difference between EMF and potential difference. Okay, so that's all said. Well, I'm going to have to then, I think this is a good time to pause this video. It's gone on long enough. So it's going to have to wait until the next video when I'll keep my promise and ask what things can affect the resistance so that Ohm's law doesn't hold anymore. This time for real, next lecture video.